And welcome back as we go ahead and jump into our next review. This time we're going to go ahead and look at exponential functions. Let's go ahead and start off with a little bit of an example here to kind of help hone this point in. As you can see here, we have a table which is kind of showing a growth of $100 at an interest rate of 5.5%. And you notice in here it'll state that it is being compounded annually. So if we look at our year 1, it says that $100 has made 5.5% interest for a total of $105.50. At year 2, that $105.50 is now have a 5.5 or 5.8% interest for a total of $111.30, which then has $612 in year 3 for a total of $117.42. In year 4, we are making $6.46 interest for a total of $123.88. Now, one thing you'll notice is that after that first year, the value in the account is always 1.055 times its value in the previous year. Notice this is the previous year column because we see that 105.50 is here, the 111.30 is here, 117.42 is here. And after n years, we can say that the value is equal to y equals 100 times 1.055 to the power of n. That 55, of course, is probably coming from this interest rate right here. Now, compound interest provides us an excellent example of exponential growth and is modeled by a function of the form y equals p times a to the x, where p is our initial investment, or our principal, and a is equal to 1 plus the interest rate, which we can express as a decimal. Now, the function has a domain of a is greater than 0, and that a cannot equal 1. You'll note that the function is, of course, an example of an exponential function, and the ratio of consecutive amounts in the table is always the same, 1.055. So if we want to define what an exponential function is, we can simply first let a be a positive real number other than 1. So, for example, it could be 2, it could be 3. And then what we're going to say that the function is equal to f of x is equal to a to x. Then I put 1 here. Well, what's 1 to the power 1? 1 to the power 2. 1 to the power, it's always going to be the same thing. So I have to have some other value other than 1 in here. And this is, of course, going to give us our exponential function with base a. Now, the domain of f of x equals a to the x, so this is just our parent function right here, is negative infinity to infinity. And the range is from 0 to infinity, because if we look, when we have a is greater than 1, you'll notice our curve is moving upward as x increases. And when a is between 0 and 1, our graph is curving downward as x increases. Now, let's go ahead and apply this to actually graph an exponential function. And what we want to do is graph y equals 2 times 3 to the power of x minus 4, and we want to state the domain and range. So, a couple things to keep in mind here. If we want to do this real easy, we can, of course, pull up our graphing calculator, and we can plug that function in. So I'm just going to do 2, parentheses, 3 to the power of x, and then I'm going to subtract 4. Let's go ahead and graph this real quick. And you can see we have what almost appears to be a straight line, which means we have a limit here. So I'm actually going to zoom that in just a little bit. I'm going to go to my window. Let's change this y minimum to, let's say, minus 5 so we can get a better look at that. And you can see that that is sitting right around minus 4. Because if we think about how our parent function was, this parent function was originally having our range had a limit starting at 0. And all this did, this minus 4, simply shifted that. So let's go ahead and state our domain and range before we graph this onto our own. So our domain is still the same. We're still moving from negative infinity to infinity. Whereas our range, you can see now instead of starting at 0, our range is at negative 4 and still moving on to infinity. So if we think about this, we have a graph that is very closely hovering around negative 4. And if we kind of come back to our graphic calculator references, you can see we are kind of having a point right here where it crosses. Oh, look at the 0 and minus 2. So I want to make sure that I am going to have my graph cross that point. And then, of course, it's moving onward and upward. That's a pretty crude sketch of that. So you could make a more accurate one. I'm just going to fix that just a little bit there, make it a little bit more representative of what we saw in our graphing calculator. Now, if we move onward a little bit, let's keep that graphing calculator handy just for a second, because let's say we want to find the zeros of the function. Zeros, of course, are going to be where we are hitting those intercepts. So if we, of course, trace this one, we can kind of get a rough idea of where this is going to be. But I want to use a new function here. let's go ahead and use the function f of x equals 5 minus 2.5x graphically. And so let's go ahead and plug it in. So I got 5 minus 2.5, and we're going to take that to the power of x. And let's just go ahead and reset our window here. We're going to take that back to the standard window just so we can see that. And you notice this time the curve is a little different than what we previously have seen, but that's okay because we have this in play here now. And if we want to find the zeros of this, there's of course a couple different ways we can do this. The first, of course, if we are using our graphing calculator, we can first start off by trying to trace this to try and see where those zeros are. So if I go ahead and start tracing this, and I can start moving this down, I can follow this down, 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 and you can see we get right around somewhere where x is just right around 2. Looks like it's trying to cross that. And the one way we can check this is I can go second, and I can hit graph here, so I can get to my table values. And right now in my table values, you can see x is changing by value 1, and you can see that is a pretty large range here. So I'm actually going to go into my table set here. And I know this is going to be around 2, so I'm going to change this table start to 2. And I'm going to change this change value. Let's change our scaling to 0.1. And then I'm going to go back into my table, so second and then table. And now I can, of course, hit the up arrow here to kind of see a little bit more where this is going to be. So now I can see it's between 1.7 and 1.8. However, a real quick way to do that is we can also kind of get a calculation. So I'm going to go back to my graph here, and what I want to do is actually perform a calculation on this. So I'm going to go ahead and hit second and hit calculate, and right here we have the option for 0. So I can go ahead and enter that in. Alright, let's go ahead and calculate our left bound. So that looks fine to me. And so we're going to then trace this down. We want to find a right bound, so we're going to say we want to look for it between these 2 points here. And I'm going to press enter again. And it's going to calculate my f0 to be 1.75. And of course this would be the 0 that we are looking for. And so our 0, that function, we can go ahead and then transfer that on over. And so we'll say that x is equal to 1.75. And we said 6, I think is a pretty good approximation. We can do more places if we need to. But this is the 1, 0 that we had for that function. Now, with that in mind, there are, of course, a couple things to keep in mind when we deal with exponential functions. Because we're dealing with exponential functions, that means we have exponents in play. And as a quick recap, whenever we have exponents, there are certain rules that we can use to help make our life easier. The first is, if we say that a is greater than 0 and b is greater than 0, we can apply all the following for real numbers x and y. So we can see with our first product rule, we have a to the x times a to the y is the same thing as saying a to the power of x plus y. And if we have a to the power of x divided by a to the power of y, that's the same thing as a to the power of x minus y. What about if we had a power here, a to the power of x to the power of y? Well, that's the same thing as saying a to the power of x times y. And if I have a to the power of x times b to the power of x, well, that's the same thing as saying the quantity of a times b to the power of x. And similarly, if I had the quantity of a over b, and I took that to the power of x, that's the same thing as saying a to the power of x divided by b to the power of x. If you're not familiar with these exponent rules, you're going to want to make sure you kind of get a good handle on them, because it's going to come real in handy as you start diving deeper into some of the different things we're going to need to know for the different rules with exponents here. Now, we already talked about exponential growth, but let's make sure we touch on exponential decay. These are functions that can also model phenomena that produce a decrease over time, such as radioactive decay. The half-life of a radioactive substance is the amount of time it takes for half of the substance to change from its original radioactive state to a non-radioactive state by emitting energy in the form of radiation. So if we look at our example here, we have, suppose the half-life of a certain radioactive substance is 20 days, and that there are 5 grams present initially. And what the question is asking is, when will there be only 1 gram remaining? So what we're going to do is first need to think about, well, what is the amount of grams after 20 days? So we have, of course, 5 grams here. So we know we have 5 grams. And if I were to take half of that, I, of course, would get 5 halves, or 2.5. And that would be just for 1 day's decay. So that is, of course, 1 cycle, so that's 20 days. Now, if I go to 40 days, that's the same thing as saying 5 times 1/2 times 1/2, which means that I would expect this not to be 5/2, but to be 5/4. And you can kind of see how the pattern is moving on here. If I went to 80 days, this would then change from not 5/4, but we'd have to multiply by another half to get 5/8, and so on and so forth. That means we can use a function here to actually help model us since we have a consistent ratio. So let's switch over to my blue here, and let's go ahead and write that function as y equals, since we know our base value is 5, we can then say that 5 times 1/2 times t divided by 20. All right. Very similar to our other formulas. Of course, t is representing the time we need. We're doing 20 because 20 days is the cycle length. And so once we have that in mind, it's from here, we can then move to find out where exactly is there going to be 1 gram remaining. And one way we can do this, of course, is to use our graphing calculator again. So let's go ahead and come in here and plot in this new function. So we're going to say 5 times 0.5. We're going to raise that to the power of, and we're going to do x over 20. So that is, of course, our function model. And what we want to do is actually have an interception here, where when there's only 1 gram remaining. So the easiest way to do this is just go ahead and plot the value 1. And let's go ahead and, I think our previous view should work okay. Let's just, or at least for starting. And let's go ahead and graph this. And so you can see here is our radioactive decay line moving through. And there's our other line, but we can't quite see it. So I'm actually going to hit zoom. I'm going to hit zoom fit, which is button 0, just to hopefully get a little better view of this. And line's moving down, moving down, moving down, and you can see it's still not quite there. So we're going to adjust our zoom here. So let's go to our window. And we are going to make our x 0 here, simply because we know that this is a value that is not going to be anything smaller than that because it's the number of days. And let's make our x scale, since we know we have a value of 20 and 40, and we're moving in that direction. Let's go ahead and make this something like 200. And let's make our x scale about 10. And I'll make the y max 10, and the y minimum we'll leave at 0. Let's go ahead and regraph that. And so now you can see we have our line moving through. Here comes our other line. So now we have 2 lines. Cool. Let's go ahead and calculate the intersection of these. So what I'm going to do is, again, do second and calculate. I'm going to press 5 to find the intersect. And it's going to ask me for the 2 curves. So I'm just going to go ahead and press enter for the first one, and do enter for the second one, and it's going to guess the point of intersection, so I press enter, and it's going to tell me the intersection is at x equals 4.69. Alright, so that is, of course, our intersection right there. So if we want to round this 4.64, we can say that's approximately going to be 46 days. So let's just go ahead and say at t equals 46 days. Again, having that graphing calculator can come in real handy to helping us find some of these different pieces. Now, we of course have looked at 2 different types of exponential functions. We have exponential growth and exponential decay. And in both of these examples, the function y equals k times a to the x, it has to be greater than 0. It's an exponential growth if our a is greater than 1, and it's a model for exponential decay if a is between 0 and 1. Let's go ahead and again apply this to another example and talk about compound interest. This is one common application of exponential growth that is used quite often. You see the things like savings accounts or some other type of financial account. Now, some accounts will pay multiple interest times per year, which increases the compound effect. For example, an account earning 6% annual interest compounded monthly is going to effectively pay 1/12 the interest every month. So you're really getting a monthly interest rate of about 0.5%. So when we look at compound interest, there is a formula that's going to come in real handy for us. And if an account begins with the principal t and earns the interest rate r compounded n times per year, we can then say that the value in that account after t years is p times parentheses 1 plus r over n, and the parentheses raised to the power of nt. All right, so let's go ahead and apply this So we can use our exponential function here. We're going to have Benny. He's going to deposit $2,500 in an account earning 5.4 annual interest. And how much is it going to be in his account in 10 years if we compound annually versus quarterly versus monthly? So the big thing, of course, to keep in mind is that compound interest formula. So P times 1 plus R over N raised to the power of N times T. So this is going to be the thing we're going to need to use. So let's start first with letter A here. In all of these pieces here, we can, of course, identify some pieces. So P, of course, is 2,500. And we know our interest rate, so our R, is 5.4. And that means we're going to put this in as a decimal as 0.054. Very important distinction there when we start working through this. So let's go ahead and set up the first one. So we have 2,500. And we're going to multiply that by 1 plus, and then our rate over the number of periods. So in this case, whenever we see number of periods, if it's annual, annual means there's only one. So again, annual is 1. And so this is simply just means we can just plug this value right in here. So 0.054. And we're going to raise this to the power of 10. Again, because n times t, and remember n we already said was 1, so t times 1. And so that should get us our value there. I'm going to come back and solve this here all at the end. Let's just go ahead and set up our other two ones. So let's just go ahead and do 2,500 times 1 plus 0.054. Now this is for the quarterly problem, which means if it's quarterly, this means that it is going to be 4 as our number of compounds. So quarterly is 4, so we're just going to divide this by 4, and we're going to raise that to the power of 40. I went ahead and did a little quick math there because 10 times 4 is 40. And for C, let's go ahead and do the same thing. We're going to do 2,500 times 1 plus 0.054. And we're going to divide that by, you can probably already guess, 12. Because now we, of course, are doing monthly, which means we need to have 12 as our operator. And again, simple math, 10 times 12, 120. Now let's go ahead and just take all these and put it in our calculator. So what I'm going to do is just pull my calculator real quick here. I'm going to slide it over so I can see my numbers. And let's go ahead and clear that out. Let's do 2,500 times, let's do 1 plus 0.054, close it out, raise it to the power of 10. Hit enter. All right, we got 4230 and 0.056. So let's just go ahead and round that up to the nearest. So let's go ahead and write that in here. So I'm going to say equals, we'll say $44,230 and 0.06 cents. All right, let's go ahead and do the next one. Actually, I'm going to switch to blue ink so we can make that a little more distinct here. I'm just going to go ahead and recall this a little bit here. Let's go ahead and put that back in. So 2,500. Do second entry, save myself some type. There we go. And what we want to do is we have to change this now because the 2,500 is going to stay the same, but now we have to say this 0.054. And remember, we have to divide that by 4. And then what we have to do is also come in here and make it so that way our final number is now going to be not just 10 anymore, it's going to be 40. So now when you press enter, we have a new number, $4,274 and 55 cents. So let's go ahead and write this one in. $4,274 and 55 cents. All right, last one. Now let's go ahead and again do the same thing as we just did, but I'm going to change that 4 that's in here to 12. Hit enter again, but I almost forgot. I got to change this 40 to 120 because we have 120 here. Press enter. Now we got $4,284.82. So let's go ahead and put that one in as well. $4,284.82. And of course, there's our answers right there. Now, one thing you'll note is the more times that we compound, you'll see that we are starting to get larger values. And that's a cool thing with compound interest. And as we look at this, the value of the account becomes greater as the number of interest payments per year increases. So if I took it from 12 and made it, let's say, 36, you'd see it even larger. But there is an important thing to note. These values aren't necessarily increasing with bound. Yes, they did increase. But if we look at them and how they increased in here, they did not become drastically larger. There seems to be almost like a ceiling that they're kind of bumping up against. And in fact, a bank can actually say, you know what, we're going to compound your interest continuously, and they still won't have a massive increase that they'll have to pay out. And this is because the number that serves as the base of the exponential function in the compound interest formula has a finite limit as n approaches infinity. So when you say 1 plus r over n to the power of n, this is actually approaching e to the power of r as n is approaching infinity. Now, the number e, which is approximately 2.71828, is a very important number in mathematics. Much like our old friend pi here, e is an irrational number that can actually show up in several different places, such as the continuously compounded interest formula. And with continuously compounded interest, you'll notice that it's very, very similar to the compound interest formula we had here, except now it's just p times quantity of r e to the power of r raised to the power of t, or as it's sometimes referred to as PERT, so p times r raised to the power of r times t. So let's go ahead and do that exact same formula we saw before, but now we're going to do it with the compound interest formula. Again, just for reference, it's going to be p times e raised to the power of rt. So if we look at Ada's account, you can see she has a very similar value. She's putting in $2,500 at 5.4% interest, and we want to find the value in 10 years. So let's go ahead and just, of course, pull us some identifying information. We know that P is going to be 2,500. We know that our rate is 0.054, and we know that our time is 10. So plugging everything into our formula, so let's say our principal is, I'm actually going to switch this over to the black ink real quick so I can distinct that. And let's make that 2,500 times E raised to the power of our rate, so 0.054 times 10, which of course we could rewrite that as 2,500 times E to the power of 0.54. All right, with that in mind, let's go ahead and just, again, grab our calculator and find out what we need to calculate. So I'm going to do 2,500 times, I'm going to use the E function here, which is right above the ln on your calculator here. And then I'm going to plug in 0.54. Hit enter. And I got $4,290 and about 2 cents. So let's go ahead and equals, switch back to blue ink. $4,290.02. So again, even with the continuously compounded, you can see there is still that limit here that we're going to be bumping up against. And limits, of course, are going to be a very important thing that we have to work with when we start moving forward with our learning.